So, till now we were discussing about a shock wave that is normal to the fluid direction. Now, we are going to discuss something that is the shock wave that is at an angle with the flow direction. Okay. So, for which are typically called as oblique shocks. Okay. We if we have systems like this where there is a sudden ramp facing the flow, so the flow is coming this direction, the flow needs to take a deviation. Okay. In such a scenario, you would face something called a shock wave, which is slightly at an angle. So, there is an angle between the shock wave that is standing here with the flow direction. If these are the streamlines, then the streamlines are at an angle with the shock wave. Okay. And the flow is also deviated a bit. Okay. So, we should be talking about the angle of the shock as well as the deflection it creates. So, there are two angles involved here. Okay. Or if we have a left body that is facing, so I have a streamline that is coming, and then it deflects, it is deflected this way. Okay. So, we are going to discuss these kinds of shock waves. Okay. So, these are again oblique shocks. So, we are going to talk about such kind of waves, for which we will go back to the first set of shock waves we know, which is our normal shock. So, we will revisit normal shock and then change that to oblique shock. So, in normal shock we had a shock and then I had a velocity that comes here and goes out. Okay. Now, we call this as let me call this as V1 and V2 instead of our term x and y to differentiate that this is a oblique shock. So, I have a velocity V1 and then I have a V2. Now, this is a velocity component that is normal to the shock wave. So, whereas my tangential velocity is 0. So, I can write this is as good as writing this as the normal component of velocity V1 and normal component of velocity V2 with V1 tangential is 0, V2 tangential is 0, and that is my normal shock. Now, to this I am going to add a tangential component. So, I have a shock wave, I have a V1n, I have a V2n. I am going to add a tangential component tangential to the shock wave. Okay. So, this is normal to the shock and tangential to the shock. V1n is normal to the shock, V2 is the tangential to the shock. Okay. So, I am going to add V1t here and a V2t here. Okay. here or here. Let me put it here. Okay, so this is my V2t. So if I have a V1t added to this particular component, then the resultant velocity would be at an angle like this, and here again I have something at an angle V2. We will show that this V1 should be equal to V2 for the oblique shock waves. V1t should be equal to V2t. Okay, we will show that analytically, or we will derive that set. But this is what it seen. So I have a velocity that is coming at an angle, hitting a shock wave, and this thing. This I can redraw in this particular fashion. So if I take my V2 to be this way, V1 to be horizontal to the plane, then that is at an angle with the shock wave. So the shock is this way. Then I have a V2. So I can redraw the same picture in that particular fashion. I have just rotated my angle by rotated my coordinates by this angle. Okay, and this is my oblique shock. So all I have done is added a tangential component to what we have already studied. Okay, that's all I have done. Okay, now some notations which we are going to follow. Beta is my shock angle, theta is my deflection angle. Okay, and obviously T is for tangential, as I have already written, tangential component of your velocity. N is the normal to the shock. Okay. So what is beta and what is my theta? So if I have a flow, then I have a shock wave that is here. The shock angle is this angle. This is my V. Okay, this is my V1 and this is my V1. This is my beta. Okay, or the angle which the flow makes with the shock is my beta. And the deflection angle is, so if my velocity is deflected this way, okay, so from V, which is going this way, my velocity is deflected this much, that is my theta. Okay, so this is my shock, beta is my shock angle, and the velocity here that is deflected is my velocity deflection angle. Okay. So we will fix this notation for the few lectures that is to follow. Okay. So if this is the notation, then if normal is this V1n, tangential is parallel to the shock, so this is my V1t, then this angle is my beta. And here the normal is V2n, tangential is that is along my shock wave. So, that is this is my V2t. So, this angle is this angle would be 90 minus beta. So, this angle is 90 minus beta, okay, which is same as this angle. So, this is 90 minus beta. So, this would be 90 minus beta plus theta. Okay, is that fine? This is theta, this angle would be this angle, which is 90 minus beta. Okay, so this and this should add up to 90. So, this is beta minus theta. Okay. So, if I redraw this, I have the shock, I have V1 and it is deflected to V2. Okay. So, the deflection angle is theta, this is my beta. So, the tangential component is V1t, is making a beta with V1, then I have a normal, so this is 90 degrees, this is my V1n, so this is 90 minus beta. So, the normal you can extend it here. So, that is my V2n, then I have a tangent that is coming here, that is my V2t, this is 90 degrees, this angle is same as this angle, which is 90 minus beta, and this angle is 90 minus this angle put together. So, that would be beta minus theta. Okay. So, now we know all the components and all the angles. Okay. So, this figure we have to familiarize when trying to do the problems. The important angles are this beta, which is the angle between the fluid velocity direction and the shock angle, and the deflection angle is the velocity which has been deflected by the shock. So, if there was no shock, the velocity would have been going straight. Now, it is deflected by theta, that is your deflection angle. So, these two angles we have to be very clear, and everything else will follow from there. Okay. So, tangential velocity is parallel to your shock, normal velocity is normal to your shock. That completes your velocity triangle from which you can find all this. Okay. Okay. Now, once we have this, we will apply our continuity equation and energy equation across the shock, like we have done for the normal shock. Okay. So, I have a normal shock, I take a control volume here, Okay. Now I have a flow that is coming here and then going this way. And then I have the normal component V1n and the tangential component V1t. Likewise, we have a normal component here V2n and the tangential component V2t. Now I am going to apply the control volume approach or the mass conservation around this particular control volume, that is around the shock. Okay. Assuming the thickness to be very small and there is no fluid that is going through the other direction, the only fluid that is crossing here is through the phase of the, so this is A and B, C and D. The fluid is crossing only A, B and C, D. Okay. There is no fluid that is crossing AC or BD. If that is the case, then I can apply my continuity equation or mass conservation equation. Which is V1n into rho 1 into A1. So, the fluid that is crossing the area, it is a normal velocity, is same as V2n rho 2 A2. Okay. Assuming A2 equals A1, assuming the control volume to be very thin, I can assume A1 equals A2. I have V1n rho 1 equals V2n rho 2. So, if I have a normal shock with velocity V1n and then I can find the relation accordingly. We have written for a normal shock Vx rho x equals Vy rho y. So, that is my equation 1. Now, I will do the apply the momentum equation to this control volume. So, I am going to rub this. X equals around the control surface rho V bar dot rho V into dA. Okay. Now, I have two components, tangential of this and normal component of this. Okay. So, the tangential component and normal component will differ only when so this would be my normal F normal and F tangential. So, F sigma F tangential equals integral V tangential rho V dA. Okay. Tangential sigma is 0, we are not considering any tangential force here. So, this is 0, we can apply V tangential into rho into this would be the mass. So, this is what we have written there, rho 1 B1n into dA1. So, this would be I can write it as equal to V2 T2 rho 2 V2n into A2, A2 and A2 cancels out. So, you end up with this equation. Rho 1 V1n V1t equals rho 2 V2n V2t. This is my tangential component 2. Now, for the normal component Fn normal is going to have the static pressure involved. Okay. So, if this is my shock, there is pressure acting on the control volume. So, the force is pressure into area, where we have assumed area to be same. So, my sigma F normal is P2 A2 minus P1 A1 which is equal to rho 1 V1n rho 2 V2n into V2n minus rho 1 rho 1n into as V1n into V1n. So, there is mass into velocity, mass into velocity. So, I would get a relation like this: P1 rho 1 V1n square equals P2 plus rho 2 V2n square. Okay. There is a sign that is missing here. Right hand side? Sorry. So, this would be A2, A1 and this would be minus. And this would be plus. So, that would take it this side, this, that side, that, and cancel out A1 and A2. So, I would end up with this equation, which is my equation 3. So, I will write down the equations here. Rho 1 V1n V1t equals rho 2 V2n V2t, that is my equation 2, and V1n rho 1 equals V2n rho 2, that is my mass conservation, which is my equation 3. Okay. Now, if I substitute 3 in 2, I would get V1t equals V2t. This is a very this is equation 1. So, substitute equation 1 in equation 2, correct? Substitute equation 1 in equation 2, I would get, I can cancel out these two terms. So, I would get V2 equals V1t equals V2t, which means the tangential component of the oblique shocks is equal, is identically same in magnitude. So, this deflection tangential component which we had drawn here would be modified such that V1t is same as my V2t. Now, that is a very powerful information we have. So, the tangential component before the shock and tangential component after the shock remains the same. Okay. So, your V normal and V1 or the resultant velocity and the normal velocity changes, whereas the tangential component remains the same. So, now we will proceed further. Now, what we will do is we will apply our energy equation. So, I will leave this figure, we will apply our energy equation with no heat and no shaft work. Your H1 plus V1 square by 2 equals H2 plus V2 square by 2. Okay. But V1 is now the resultant of this. So, H1 plus V1n plus V2 V1 square plus V1 T square by 2 equals H2 plus V2n plus V2n square plus V2T square equals 2. So, this is my equation 4, V1T equals V2T is my equation 4. So, now if I substitute equation 4 here, my V1T square is same as my V2T square. So, I can cancel that out. So, I would end up with this equation, which is my equation 5. So, my energy equation looks same as my normal shock equation with the component V1n. Okay. So, as if I get the component V1n, then my energy equation I can use the normal shock tables or the normal all the information I can get from here, and then I can substitute this also. Here the momentum equation also looks same with the normal component. So, I can use essentially I can try to use the normal shock tables wherever possible, and that is what we are trying to get into. Okay. So, if that is true, then we can proceed further and define our Mach number. Mach number is V1 by A1. If I define Mach number along the normal direction, this is V1n by A1n. So, V1 normal direction is this component of the V1. So, it is sine of deflection angle, correct. It is sine beta, it is cos 90 minus beta, which is sine beta V1 by A1, correct. Oh. Okay. So, my M1n is nothing but V1 by A1 into sin beta, which is M1 sin beta. Okay. Now, from normal shock we know that this has to be greater than 1 to have a shock. So, my M1n should be greater than 1 for a shock, or M1 sin beta 1 should be greater than 1. or your sin beta should be 1 by m1, okay, or equal to greater than or greater than 1 by this thing to have a shock, which is beta is sin inverse 1 by m1 to have a shock. So, if I define my beta to be this, then it has to be equal to or greater than to have a shock. So, it is greater than or equal to this to have a shock. Okay. Now, this is also, this definition is also my Mach angle, which is Mach angle mu. Okay. So, if I have a oblique shock, so this is my shock angle. Okay. Okay. The pardon? Oh, okay, on this side. This would be my beta. Okay. So, this beta has a limiting value of my Mach angle. So, if my beta, I cannot have a beta smaller than my Mach angle. So, beta should be greater than sin inverse 1 by m1. Okay. It has always should be greater than m1. m1 is this. Okay. So, if my beta is smaller than this, I cannot have a shock angle, because m1n should be greater than 1. So, if I use that condition, I would end up with this condition to have my limiting value. So, this is my limiting condition. So, beta should be greater than my Mach angle for oblique shock. I cannot have a shock inside my Mach cone. That is what it essentially means. Okay. So, this is when m equals 1. Okay. So, the limiting condition is when m equals 1. So, when m equals 1, you anyway do not have a shock. So, it is and Mach angle is a coalescence of all the waves that is generated by the sound waves. So, this surface, when you have this condition, is also called a Mach wave because of that reason. So, it is a wave that is generated, and it is also the shock wave that is there. So, in either way it is the limiting condition. So, this is one limiting condition. The other limiting condition is when beta equals 90 degrees. So, when beta is 90 degrees, your oblique shock is m1n is same as your m1. Oblique shock is also your normal shock. Okay. So, the oblique shock angle goes from, for example, if I have a shock something here, this goes from beta to 90 degrees. Okay. So, in between this region is my oblique shock angle. Okay. So, it has to be greater than mu and less than 90 degrees. Okay. So, beta lies between greater than mu and less than 90 degrees. okay, greater than or equal to this. Equal to 90 is normal shock. So, beta should be between this. The beta max is 90 degrees, beta minimum is mu. Okay. Next class we will try to derive a relation between beta, theta and your m, the Mach number. For a given Mach number, can we relate, can we get a unique value of beta and theta? Okay.